Okay, in this example, we're going to do a symbolic derivation, finding the center of mass of a cone of uniform density. Here, our cone lies along the z-axis, and so we know that our step is going to be, our key idea is going to be defined. So use the definition of the center of mass. Okay? And specifically for a solid continuous object like this cone here. All right, it need not have uniform density, but that does make our work easier in this problem. Solid continuous object. Okay, and what that's going to look like then is just z center of mass is then going to be x, or in this case z dm. But of course we have the 1 over the total mass in the front. Okay, so like so. Over the total mass of the cone. All right, so I'll show here that the total mass of the cone is uppercase M. Okay, and then the other thing that we will need here is we also are going to need, in the symbolic example, and this would also be true of any problem with a non-constant density object, we'll need a second integral, which is just the total mass is just going to be dm. Okay, and in both cases, dm here is the mass element. All right, so we can show that dm is a mass element. All right, so now let's get started with the problem. Okay, so CCM, the thing we're trying to solve. All right, 1 over m, okay, and then z dm. Okay, well, we can change that mass element to something that involves the volume of the cone, and then we'll basically make connections here to actually have something that we can integrate, because as written we can't integrate across mass because we don't have the right variables to do so. So what is almost always the next step in one of these problems is to replace dm with rho dv. Okay, where rho is the density of the cone, and in this case, since it's a uniform density, let's highlight that, then all right, so then what we have is that our density is just going to be, we just have, so it's going to be kilograms per cubic meter, so it's just going to be the total mass over the volume of the cone. Okay, and those are constants, so they will come out right out of the integral. All right, so our next step then is to move forward. We'll just keep going back to the definition of the center of mass. All right, and we'll just continue to substitute in the information we have. So now this is going to be z m over v, which we'll pull out in our next step, and then dv, right? And all I've done here is just replace rho with m over v. Okay, so then what do we do with dv, right? Because we still have the issue that we are integrating in terms of z, but this is in terms of v. So we need to express the volume in terms of z, the vertical coordinate. Okay, so what does that take? Well, the first case in simplifying this and re-expressing dv is to actually think about this picture above, right? So we show here this mass element, right? Well, dm is equal to rho dv, right, as we already pointed out. Well, that means that in a sense we've taken care of the rho, that uniform density, and obviously we can see here, or hopefully we can see that if this problem was made more complicated and we had a non-uniform density, simply we would not have a constant here that we could pull out, but instead we'd have another function, which we just have to include in our integration and in taking our antiderivatives properly. But here, no worries. We just need to re-express dv. Well, dv is a particular little volume element now, right? And it's got thickness dz, and it's got cross-sectional area pi r squared. So that means that dv is exactly pi r squared dz. Okay. So I got 1. So we have our 1 over m and our m over v, okay, and then we're going to have z, and then pi r squared dz. Okay. Now you might say, oh, we should then pull out the r squared in the front, and then we can just integrate across z. But there's a major issue with that. R, which is the radius of our little mass element, well, it's not constant. It's changing. It's changing as we move up and down the cone. So that means that R has some sort of dependence on Z. And this is the key step of solving this problem conceptually, is thinking about what is the dependence of R on Z. Okay? And what that is, right? So we'll say and what that dependence is that little r is big R over h times z. Okay? Well, how do we know this works? Well, little r is 0 when z is 0, and when z is equal to h, little r is equal to big R, right? So we'll say with r equaling 0, when z equals 0, and r equaling big R when z equals h. So basically we've just come up here with a function, right? That this right here is our function that that shows the dependence of r on z, and that meets the two limiting cases, r of 0 and r equal to big R. And that's the type of function that we have to come up with a lot of these types of problems, for center of mass problems, for moment of inertia problems, and it's just finding the two extremes, the 0 and h in this case, and making a function that meets that criteria. Okay. Also, I'll point out one thing I said incorrectly a minute ago is that we had to worry about finding this the second integral. That would be the case if we had non-uniform density. But I'll say here, so that we don't have to worry about that, and the reason is, so not a concern, because density is constant. Because then we don't have to find out what the total mass is. It's simply it's just a constant, right? And or rather the mass comes out of the center of mass integral, and so then what we have is our masses just cancel out. And this v here will just be the formula for the area, or rather volume, of a cube, right? Which we'll deal with in one of our final steps. Okay, so now we'll go back to our integral. And we got 1 over v in the front. And then we're going to have z pi r over h z squared dz. Okay. Then we're going to have, again, 1 over v. Our pi is going to pull out. We're going to have an r squared over h squared also come out of the integral. And that's just going to leave us with z cubed dz. Okay. All right. So we're going to be wrapping this up in the next couple steps. Okay. Actually, this is a good point to point out the volume of a cone, and this would just be something that you would look up, right? It's a step of the problem, or background knowledge. And it may not be the most common of volume formulas, but right here we have the volume of a cone, pi r squared h over 3. Okay, so we're then going to substitute that in. All right, so we're going to have, it's 1 over v, so I'll just go ahead and take the reciprocal. So z, center of mass, is going to be 3 over pi r squared h, and then r squared h squared, and then we have our, we'll do our any derivative here, or just, and we're going to be, and we're going to be integrating from 0, and this is actually quite important, from 0 to h, okay? Because, right, as we look here, you know, that's our z is going to vary from 0 to h. Okay, and so then this will become 1, or just z to the 4th over 4. We'll just show the integration here from 0 to h. Okay, go ahead and cancel out the r squareds here, this step. And then so we're going to have 3 over pi h cubed h to the 4th over 4. Okay, and that will cancel with all except the 1h in the numerator. And so then our final value is going to be 3 over 4 pi h. Okay, so that is the location of the center of mass along, in this case, the z-axis, just along the long axis of the cone, and it tells us exactly where it's located. And in terms of a decimal, oh, I see a mistake I made. I started wondering about why we had it was a pi in there. I was like, oh, maybe that's right, but it's not. So we see that I dropped the pi up here. All right, so we'll just put it back in at this step. And we'll see that it cancels. All right. So this was this pi here, whereas the other, our other value of pi came from the volume formula for a cone. So that should have canceled in that step. So then we should have just had 3 here, not 3 over pi. And so then our final value is not 3 over 4 pi, but just 3 over 4. All right. And the reason it wouldn't make sense for it to be 3 over pi, regardless of it, kind of being an odd result, is that 3 over 4 pi is 0.24, which would have given us a value that would be quite close to the bottom, right? 0.24h, right? Just 1/4 of h would be around there. That wouldn't make sense for the center of mass. Obviously, as the cone gets thicker, that means the center of mass has to be closer to h than it is to 0. And sure enough, it's 3/4 h. So that's a nice clean result. And, well, as a decimal, it's just 0.75. All right, so there we have it. The center of mass of a uniform density cone is 3/4 h. Thank you.